that gives you a consistent truncation to the theory that you see on the slide over here. This was done by Donis Gauntlet and Wadra. So I'll show you that. The one thing I should mention is I did not actually have to do S7. I could have replaced it by what's called a Sasaki-Einstein manifold. And the 7-dimensional Sasaki-Einstein manifold is kind of weird, because normally I think of preservation of supersymmetry as something to do with Kähler manifolds or something that's even real dimensions. This is an odd dimensional manifold. But I decided to write what's called a cone over Sasaki-Einstein, dr squared plus r squared times something over here. Normally this would be like a sphere. Dr squared plus r squared times a sphere is a natural way of writing flat space in spherical coordinates. I can replace the sphere over here by something slightly different, like the Sasaki-Einstein manifold over here. This gives me an even dimensional space, and the Sasaki-Einstein manifold is basically what it is that if this thing here is Ricci flat and Kähler, so if this is sort of non-compact Calabi-Yau, now what's inside here is the Sasaki-Einstein manifold. This is what you need to preserve some fraction of supersymmetry. And so instead of having CP3 times the U1 fiber over here, I can just have what's called a Kähler-Einstein base over here times the U1 fiber over here. So this generalizes the 7 sphere or the squashed 7 sphere. And I'm doing this without being explicit, just understanding the existence of these type of Sasaki-Einstein manifolds. Well, one thing about this Kähler-Einstein base is it has a Kähler form and 1-1 form. It also has a holomorphic 3,0 or holomorphic n,0 form, which you can call capital omega, something like the Calabi-Yau form, except that it's not necessarily Ricci flat, it's Einstein, so it's not closed. Well, this defines an SU-n structure through these type of structure equations, like that. It is the existence of J and omega that allows us to write down a nice consistent truncation that allows us to retain the massive cosine level 2. Idea is these define a form, so these are invariant tensors. And I have, well, I wrote them in complex notation, but basically I have 2 form J and 3 form omega over here. And so I can take my fields and expand on a basis of invariant tensors. And this is what I mentioned. Oh, Continent, Kimber, and Audra, I'm sorry, I got the names sort of mixed up a little bit. These guys did the breathing mode. Sorry, these guys did the massive truncation. And so what we want to do is write down an ansatz for the metric and for the 4-form field strength. The metric is very simple. I take my ADS4 metric over here. I allow it to have a varying G mu nu. The Sasaki-Einstein metric has my fiber over here over a Kähler-Einstein base. And the Kähler-Einstein base, let me remind you, has invariant tensors J and omega. I can turn on a breathing mode, which is V over here, which is the breathing mode multiplying the 7-dimensional kernel space. That puts myself into Einstein frame. And then there can also be a squashing mode, which is the relative distortion between the base and the fiber over here, which is parameterized by little lowercase u. This is a U1 fiber. So in addition to d eta equals 2j over here, I can also throw in a space-time gauge field, which I can think of as a gravity photon. A1 as a 1 form. So the summary of fields from the metric over here is very simple. There's a 4-dimensional metric G mu nu. There's a 1 form over here. I call it a vector field mu nu. There's a squashing mode U, and then there's a breathing mode V over here. So 1 metric, 1 vector, and 2 real scalars. The 4-form field strength turns out to be a little bit more complicated. Since I have J and omega, I'm going to take a 4 form, I can expand in a basis that includes J and omega. So you try to do it at least a little bit systematically. You see, this is four forms. It has four indices or four legs. They can live entirely in space-time. So I have a four-dimensional space-time, which is just a volume 4. It may not be a constant, so we're going to multiply by a scalar function. This is f of x. This is a possible f of x scalar, which are copied down over here. I can also have a 3 form in space-time, wedged in 1 form in internal space. 3 form in space-time, let me just call it H3. Internal space means I want a 1 form over here. Well, there's no standard 1 form on the base over here, but there's a 1 form fiber eta, which is what this is over here. And since I've gauged it eta plus a, it's convenient to write it as eta plus a. I can have a 2 form in space-time, wedged to 2 form in internal space. There's an obvious 2 form in internal space, which is J over here, gives rise to that term over here. I can also have 1 form in space-time, 3 form in internal space. 3 form in internal space, omega is a 3 form, which is what gives you these terms over here. It's a complex 3 form. It's a 3, 0 form, so I can have its complex conjugate as well. Sorry, it's this term over here is a 3 form. I can also have J wedge eta is also a 3 form. Or I can have a scalar in space-time wedged to 4 form in internal space. 4 form in internal space I can create as J wedge J over here. Or I can create as omega wedge eta over here. So just in terms of a basis of invariant tensors, this is the best you can do. And from a four-dimensional point of view, you can label all the possible fields. This time the metric is relatively simple. The reduction of F4 is a little bit worse in terms of the complication. What these people do next is to say, well, this is my oscillator. I write down the most general oscillators I can think of compatible with the symmetries I'm trying to preserve. After I do that, I should start plugging into equations of motion. There's a 4-form Bianchi, 4-form equation of motion, and Einstein equation. Einstein equation is usually the worst, so we say that for the last. Let's look at the 4-form equations of motion. Or at least we can look at the Bianchi identity first. And you can look at their paper for more details, including where they show you how it's done in their appendix. But the end result is something like that. All these things, H1, HCH3, B1, well, H1, HCH3, things like that, basically showed up in the 4-form oscillators. And by demanding Bianchi, you can see things like DH3 equals 0, so you write H3 as DB2, and so on. And you work your way through the Bianchi identity in its various space-time times internal space components. You write it up kind of like that. There's also the equation of motion, which gives you equations of motions for these various fields, like D star H equals so on. So there's one component of the equation of motion that's very interesting, which is more like a constraint. F was the factor multiplying the volume form. And it turns out to satisfy the equation of motion, you need to have something of this nature. There's a little bit of a normalization involved. But if you imagine little h and chi are scalars. If I didn't have any scalars, if I turned off the breathing mode V over here, I get F equals 6. That means the 4 form has as leading component 6 times the volume form. Earlier I wrote down 4 form as 3 over L times volume form. But of course, what they've done is they've chosen the L equals 1/2 normalization here. So you can see this is a generalization of the Freund-Rubin oscillators. F equals 6 as a constant is Freund-Rubin. Turn on the breathing mode, and then turn on some additional scalar modes as well. But when all is said and done, if you've solved the Bianchi identities, and you put in this constraint over here, the 4 form gives you 2 form, 1 form, and 3 scalars over here. Chi is a complex scalar. Counting the real degrees of freedom, I wrote it twice like that. Chi plus this complex quantity. And the somewhat hard work is to organize all this information, things like that, into an effective Lagrangian. It turns out the Lagrangian looks kind of like that. I didn't write down all the interaction terms here. But the Lagrangian written over here gives you four-dimensional equations of motion. If you solve the four-dimensional equations of motion, you're guaranteed to have a solution to dimensional supergravity. Now, part of the complication for the Lagrangian is because it's a nonlinear reduction. Part of the complication is because they have a bunch of fields floating around. But it's fairly straightforward to understand what's going on. Einstein Hilbert. They have scalar fields. These are kinetic currents for scalar fields. du squared, dv squared. Obviously, it's not canonically normalized. dh squared, d chi squared. And then he had A1, grab a photon, F mu nu squared. You had B1 and B2 giving rise to H3 squared and H2 squared like that. There's a scalar potential. There's a mixing term over here, and then there's higher interactions as well. Because you have a bunch of scalars, you have 5 scalars, your potential has a bunch of terms involving these different scalars that have these exponential sort of factors like that. Here, there's metric, 5 scalars, and 2 vectors. There was this B2, but it can dualize to something that looks like a supergroup, a scalar, giving mass effectively to B1 with the complication of having a little bit of mixing involved. So if you've been thinking about Kaluza-Klein reductions and consistent truncations for some time in the past, you might think this is actually very remarkable. When I saw this come out, I thought this is very remarkable. Because normally we thought you can truncate just sort of the 0th Kaluza-Klein level, the supergravity sector, you have to throw out the whole KK tower. For n equals 8 supergravity on the round subsphere, you probably do have to throw out the whole KK tower to get a consistent truncation. But in this subsector, where you truncate to SD4 singlets, basically you can actually keep part of the level 2 tower. You can have a little bit of a massive mode left over. So this is a consistent truncation with massive modes in the KK tower. So it's a little surprising to see that, but the symmetry principle guarantees that it works. This potential is a little bit complicated, so let me highlight the features of this again a little bit, which means I could expand this around the vacuum solution. So expand it for small fluctuations. And this is what you get. Cosmos or constant term, minus 24, which gives you the correct L equals 1/2 radius. And then 5 scalars, U squared, V squared, H squared, and complex scalar chi squared like that. The numbers over here, 42, so that came, those numbers disappeared by canonical normalization, and you're left with these terms over here that I copied over as masses of these scalars over here. If you plug that into the ADS sort of mass and E naught formula, you find out the scalars with these masses correspond to E naught equals 4, 6, and 5. Squashing mode, breathing mode, and additional modes over here. So I showed you the table of SD4 singlets. I copied it down over here. However, this time I didn't write down the fermions as I ran out of space. This is the bosonic stuff only. There's a Kaluza-Klein level 0 over here, which is a graviton and graviphoton. And Kaluza-Klein level 2, which is the massive vector multiplet. So these 5 scalars organize themselves like that. Squashing mode U, breathing mode V, and then the additional scalars show up. What I didn't highlight before was I decomposed SO8 into SD4 times U1. U1 means I still have U1 charges. I'm not truncating to U1 singlets. You can truncate to SU4 singlets and U1 singlets. Basically, you just truncate it to singlets of SO8. So we keep the U1 charges. And so there's two scalars over here with non-zero U1 charges, which matches up very nicely with the complex scalar chi. So it all ties together. So there's a few things that we may or may not have learned. One thing is we truncate to the singlet of some internal isometry group, you end up with consistent truncation. Singlets of SO8, you get the bosonic breathing mode truncation. Singlets of SU4 inside SO8, you get this N equals 2 massive Kurzweil truncation. Or in some cases, if you just kept the supergravity or KK level 0, it appears that they have a consistent truncation without an obvious symmetry increasement. We can ask a little bit, are there some sort of guiding principles for consistent truncations? Are there some criteria for consistent truncations? And I'll give you one of them over here, which is to show how delicate or how tricky it can be to find a non-trivial consistent truncation. And so this argument starts out as a linearized argument, but also sort of applies to the nonlinear case, because if you can't get the linearized truncation to work, you're not going to get the full nonlinear one to work as well. So let's suppose we have, to include a Klein reduction, where I have a lower dimensional space over here, and an internal manifold, which are right. And I suppose it has some isometry groups, which is generated by these killing vectors K. So this is turning on graviphotons, and turning on, I'm gauging the isometries of my internal space. So S7 is SO8 isometry. I can think about this as gauging my SO8 isometry, getting SO8 gauge fields out of the reduction. But just more generally, I have some isometries, I gauge some isometries. The linearized KK level, at the level of a linearized KK unstops, I might write down something like this. Now, I can plug that into an Einstein equation. And so I plug this into the 11-dimensional Einstein equation, or the higher dimensional Einstein equation. The lower dimensional part of that should give me something like a lower dimensional Einstein tensor. If I did a sphere reduction or a Ford-Rubin compactification, I might have a cosmological constant term. An important feature I want to highlight is the graviphotons over here will reduce to give me effective stress energy tensor, f squared minus 1/4 g mu f squared, which is good. However, the gauge fields here are attached to killing vectors of my internal space. So when I actually do the Kaluza-Klein reduction, I end up with the stress tensor of my gauge fields over here, but attached to a bilinear and killing vectors over here. This Yij being defined. Like that. The left-hand side is the Einstein tensor constructed out of my lower dimensional metric over here. This is a lower dimensional quantity. There's no Y dependence over here. There's no internal space dependence on the left-hand side. The right-hand side has killing vectors, which may or may not have Y dependence over here. If the killing vectors here depend on Y, which they do for the non-abelian symmetries, then I have Y dependence on the right-hand side, no Y dependence on the left-hand side. That would be inconsistent. The only solution is not equal to 0, not equal to 0. So consistency of a reduction here with non-trivial killing vectors doesn't really work over here. Because I have Y dependence on the right, no Y dependence on the left. This is what happens on the sphere. If I wrote down the 7th sphere over here, 80 is 4 times S7, the equation like that tells you it's inconsistent. But of course, I was just spending the last hour, almost hour and a half or so, talking about 7th sphere reductions. And I was never trying to say that ADS, I was never trying to say Freund movement is inconsistent, because it's not. So there is something that happens. This is only half of the story. The other half of the story is the question, how can sphere reductions be consistent if I just prove to you that they're inconsistent? The other half of the story is the four-form field strength. The four-form field strength sets up the Freund movement compactification with the volume term over here. However, when you gauge the isometries of the seventh sphere, the ansatz you should use for a four-form also includes the gauging over here. These are the non-abelian gauge fields, F mean U's. So if I turn on some graviphotons in the metric, in order to make the reduction consistent, I also have to turn on the graviphoton field strengths in my F4 reduction. These are the same killing vectors as I had on the other slide. Well, that's D of them. It's an exterior derivative of the killing vector is written as a one form. So dk is a two form over here. And so I need a conspiracy between graviphotons from the metric and graviphotons from F4. They're not independent gauge fields. It's the same gauge field. It's the same graviphotons that shows up in the metric. When I put that together, I can end up with a consistent truncation. What that does is if I go backwards over here, this is the four-dimensional stress energy tensor that came from the reduction of the 11-dimensional Einstein tensor, which brings in the graviphotons over here. I also have to include the stress energy tensor coming from the four form, which means this Yij has two components. Yij has this part that came from the metric, plus it has a second part over here, which comes from the four form. So the metric reduction gives me this, which I had in the previous slide. The four form reduction gives me this term over here. I still want capital Yij to be independent of Y. I still need this to be independent of Y to match with the left-hand side of the Einstein equation. But this time it actually works. It's non-trivial. It's highly non-trivial to say this plus that equals a constant independent of Y. But it does for S sub. It also does for S5, S4. The known consistent sphere reductions all solve this equation over here, being proportional to constant delta Ij. So the sphere reductions are consistent, but it's a very delicate consistency that the killing vectors on the sphere have to work in just the right way for this. This tells you if I replace the sound sphere with other objects, and I demand consistency over here, it can be highly non-trivial. Let me give you an example of that. If I had something like ADS5 times S5, it turns out I can do something like replacing S5 by T11. That's sort of the base of the conifold. And so ADS5 times T11 compactification is supersymmetric. T11 is sort of a version of a five-dimensional Sasaki-Einstein manifold. And T11 has ST2 times ST2 times G1 isometries. And what happens is the U1 can be gauged. This gives you a five-dimensional supergravity theory, ADS5 over here, with a five-dimensional graviphoton. So it's five-dimensional n equals 2 with a graviphoton coming and gauging this U1 over here. However, because T11 also has SC2 times SC2 isometries, you might say, what if I turn those on over here? The Kaluza-Klein spectrum, the linearized Kaluza-Klein spectrum at the lowest level has gauge fields for SC2 times SC2. The ADS5 gauge fields correspond to global symmetries in the four-dimensional dual theory. And so the linearized Kaluza-Klein ansatz tells you there are SC2 times SC2 gauge fields. However, I just proved to you that there's a consistency condition for gauging the isometries of SE2 times SE2. And it turns out that it fails in that example. And so the consistency condition basically tells you you cannot obtain a consistent truncation keeping the SE2 times SE2 gauge. Those have to be truncated the way to just basically pure equals to supergravity with the U1 gauging. So it's non-trivial, and to me a little bit of still an outstanding question of when can you have consistent truncations, when can you not? So the question is sort of, are there other principles for obtaining consistent truncations beyond going to a singlet sector? I don't know the answer to that, but it's certainly something, at least to me, is a bit of a puzzle and possibly worth thinking about. So I'm just going to wrap up. I'm basically done. But just to give you a brief sort of summary, because I did tell you a little bit about compactifications and the things. The thing we can do here is we relate different supergravity theories in different dimensions. We can also relate theories with different amounts of supersymmetries. By having partially broken supersymmetries, compactifying on Calabi-Yau, K3s, and Salsa K eyesites, things like that. Usually, we would have a Hochfluss-Klein tower, but many times you can find consistent truncations. We can truncate the singlet sector, always works. We also believe truncating to the supergravity sector, which means if you want to truncate to the n equals 8 supergravity in 4 dimensions, it appears to be consistent. Truncate. So the T11 compactification gives you n equals 2 supergravity in 5 coupled to matter fields. SE2 times SE2 are sort of vector fields of matter. You cannot retain the SE2 times SE2 fields in a consistent truncation. We would truncate to the pure supergravity sector. That is consistent. Questions, are there any other possibilities? And this is still, I think, a bit of an open question. So with that, I'm going to end. And I'd like to just flash up one more slide with some possible references. But also to say, thanks to organizers for putting this together. And I think it's been a very nice and rewarding experience to be able to give these lectures. I hope you've learned something as well. Thank you.
Other questions? So I have a question. So do you have a separation of scales in these new compactifications?
In this massive KK truncation or something?
Yeah.
There's no separation of scales. It's still.
So you still have the same problem that the extra dimensions is coming in at the same scale as
the extra dimensions still come in at the same scale as the ADS sort of radius. So from a more physical point of view, if you really had this as a compactification, just because I can write down a consistent truncation doesn't mean I'm forced to stay in that sector. I can presumably start exciting the other states as well, because they'll be very light.
You always first derive the equation of motion, the reduced equation of motion, then by the action, would there be something wrong if you just start with the high dimensional action and plug in the other sets with given dependence on the...
That's a very good question. Because we ran into trouble a few times reducing the action. It feels very natural. You have 11-dimensional action or high-dimensional action. You put your reduction offsets. You stick it in your action. You integrate out your extra dimensions. And you get a lower dimensional action. What happens usually is if you have, in some sense, the correct ansatz with the right, which is designed sort of to not excite sort of the other fields, then you get the right answer. But in many cases, if you're not led to the right ansatz, you can actually get sort of inconsistent results by reducing the action. For torus reductions, it always works. But for these sort of flux type reductions, I don't have, again, a precise principle for why